Hello, Apurv Ranjan. Hello, Apurv Ranjan. Hello, Apurv Ranjan. Good evening. I
Good
was just
evening.
waiting for at least one person to start.
Good
Okay,
evening,
who
sir.
come? Good. Good evening. Okay, then. Shall we just wait for another 2 minutes?
Sure, sir.
Yeah, because you are alone. Let us see at least one more member is joining.
Mhm.
Apurv Ranjan, which state do you belong to?
What, sir?
Which state you belong to?
I belong to Bihar,
Bihar. Capital
but
itself or
current.
away from?
Yeah, yeah.
Capital of Bihar, Patna itself or away from Bihar, Patna?
Uh, I'm towards the, you could say, the western side of Bihar.
Western
Towards,
side.
yeah,
Mhm.
towards Banaras, Varanasi.
Oh, you're bordering with UP.
Yeah, border is with UP.
Okay, okay, okay. Fine, good. Okay. No one seems to be joining. Well, very good. Once again, good afternoon. Welcoming to Contact Session 9. So today we are going to have the topics of again finding solution to system of linear equations, but by indirect methods. So what do you mean by indirect method? We had seen in the last session by Gauss elimination method, that is considered to be direct method. So what do you mean by indirect method here? Just for a broader classification, we say that is direct method. So what is there in indirect method? Actually, it is nothing but iterative methods. You know what is meant by iteration. So you start with an approximation, you keep on fine tuning for better results until you reach a comfortable, reasonable solution close to the exact one. So that's what we mean by iteration. You filter, you keep on approximating towards the goal. So that is more of aiming for better and better results. And that is the iterative methods. So iterative methods, according to your syllabus, we are going to have two types or two methods rather known as Gauss Seidel, named after two mathematicians. One is the famous GAUSS Gauss or Gauss Seidel, Seidel. So it is named after two mathematicians, Gauss Seidel, very famous. And another pair is again Gauss is there with Jacobi, the same mathematician, German mathematician, is again joining hands with another Jacobi so that it becomes Gauss-Jacobi method. So these two are coming under iterative methods. We'll see one after another. has happened? So as I have I've already mentioned about iterative methods, Gauss-Seidel and Gauss-Jacobi methods. And of course, we will also be talking about convergence. So convergence is again nothing but here going close to the exact solution. Of course, you know very well convergence and divergence of sequence of elements and hence series of elements. Here, it's not exactly that kind, but anyway, you know very well what do you mean by literally convergence means it is coming closer, coming to a point, meeting at a point. So here it means converging to or going close to the better approximation. And of course, we have some conditions for these two methods as to how it is converging to the exact solution as rapid as possible. And in that sense, of the two methods, which is better, we will see that. So the Gauss elimination and its variance in the sense, of course, we just have listed about three variants like partial pivoting, complete pivoting, and scaling. And of course, according to your syllabus, I said in the last session itself, we will not be bothered about complete pivoting and scaling. So we had only partial pivoting. So that's why we just mentioned that it's variance. So it is by Gauss elimination, we just have only one method that either plain or if at all we have that partial pivoting. And that of course very important. In the last two sections, we belong to the direct methods for solving linear system of equations. These are methods that give solutions after an amount of computation that can be specified in advance. So we go about reducing into echelon form, and then we have some methods in identifying the pivoting and then reducing into finally, of course, by back substitution. So first we do elimination and then we go by back substitution. So in all, whatever be the variance, in all, it is the direct method where we have some set of computations. In contrast, in an indirect method, we start from an approximation to the true solution and, if successful, obtain better and better approximations from a computational cycle repeated as often as may be necessary for achieving a required accuracy. So the repetition is made necessary depending upon the nature of accuracy that we are aiming at. So that the amount of arithmetic depends upon the accuracy required and varies from case to case. In some problems, actually, in practical problems, are according from exam point of view, some solving of system of equations may demand about 7 or 8 iterations. But for the marks and the time kept in mind, then sometimes it may be given like do the iterations up to uh, 3 times or 4 times. So that means we have to stop over there and then give the solution at that time, whatever, say at the end of the fourth iteration or fifth iteration, whatever it is. Otherwise, in general, we are supposed to do the number of iterations and where will you stop? That is important, isn't it? So you will not be exactly going to the roll number or the whole number that we need to achieve. Like for example, supposing the solutions are x equal to 1, y equal to -2, z equal to 3, something like that. So you may not exactly get 1, -2, 3, you may have 0.999 and then minus 1.9998, something like that. So keeping those two approximations very close to each other, where you will see at least those two iterations, say fourth iteration, fifth iteration, are so close to each other, almost the same. maybe fourth or fifth decimal places are slightly different. You can stop doing the iteration and declare the same values, or you can just approximate it around it. For example, if you have 0.9998, you can say 1 minus 1.9997, you can say 2 minus 2, something like that. So that if you, as usual, substitute back in the left hand side of any of the equations or all of the equations, you can see that it is equal to the right hand side. That's it. Okay, so here we are more interested in the approximation as better and better. Okay. We apply iterative methods if the convergence is rapid. If matrices have large main diagonal entries, as we shall see, so that we save operations are compared to a direct method. So here, the convergence here is nothing but the how. So you have, for example, like the first iteration, you will have, say, x value, x1 value, 1.3. And then you will see in the second iteration, it is 1.7. There will be a jump. There will be 1.3, 1.7. Practically, it is not that much big difference. But in approximation, it is more, isn't it? And therefore, but again, if you go to, so don't immediately say that 1.7 is the correct answer. If you go to third iteration, it may be 1.723 or 1.75, something like that. It will be, the convergence will be going slow, and then at one stage it gets stopped. In the sense, they are close to each other so that you can declare that is the solution. So that is what we mean by convergence. It's rapid. We also use iterative methods if a large system is sparse. Sparse means less in quantity. It's almost like a scarce. The quantity, the quantum of things that you are having is scarce, means the commodity is very scarce, means there is some limited quantity. It's a less in quantity. That is, has very many zero coefficients, so that one would waste space in storing zeros. For instance, 9995 zeros per equation in a potential problem of equations in unknowns, with typically only 5 non-zero terms per equation. Anyway, don't bother much about all these things. So you have the convergence to be rapid if matrices have large main diagonal entries. So you are going to see naturally when you are going to solve a system of linear equations of the form Ax equal to B matrix equation, where A is the coefficient matrix. And if you find the principal diagonal elements, the main diagonal elements, the leading diagonal elements are large, so naturally the convergence will be rapid. That means you don't need to go for very good more number of iterations, so that you save time. So that is how it is better. Now, just look at, just to have an idea about this kind of iteration. What is meant by? How do we go about? Suppose you take an ordinary linear equation solving 7x equal to x plus 18. We know very well 7x minus x, 6x equal to 18, or x equal to 3 in a usual way. Now, how to do it? By iterative procedure. So, iterative procedure, the consecutive term or the next term is depending on the function value of the previous term, isn't it? In general. So, xi plus 1 equal to f of xi with x1 given. So, in the iterative method, what is more important is that, as you know, the procedure that when you are finding the next term, it depends on its previous term and so on. You should have some initialization. You should have the starting point. You should have the initial approximation. So with the x1 given, supposing the sequence of terms being x1, x2, etc. Okay. Now, 7xi plus 1 equal to xi plus 18. Therefore, our given problem can be made to be 7 xi plus 1 equal to xi plus 18. So xi plus 1 is f of xi. Okay. x1 equal to 1. We initialize the first term to be 1. So what is x2? 7 x2 is equal to 1 plus 18. Because x1, 7 x2 is equal to x1 plus 18. That is 1 plus 18, 19. So 7x2 equal to 19 means what is x2? 2.7143. What is x3? 7x2 is equal to 7x3 is equal to 2.7143 plus 18, that is 20.7143. Therefore, your x3 will be your 20.7143 divided by 7. You get 2.9592. The next term, 2.9942. Look at the way the convergence goes about. X5, 2.9992 and X6, 2.9999. And you can stop. Almost it is converging to X equal to 3. Isn't that? Right. So that is the original solution, exact solution, or true solution, whatever way you call it. So then the same problem, suppose you are interpreting this way, what will happen? See, how you formulate the problem in iterative procedure is also important. Suppose you write xi plus 1 equal to 7xy plus minus 18. See, that way also you can think, isn't it? You have the same equation. We have not changed the equation. 7x equal to x plus 18 is naturally 7x plus xi plus 1 equal to xi plus 18. As it is, we are solving. And we are able to see that by various iterations, once, twice, thrice, etc. At the sixth iteration, we are able to get the better approximation converging to x equal to 3. That is the exact solution if you do it ordinarily otherwise. But supposing you rewrite this way, xi plus 1 equal to 7xi minus 18. Okay, same equation. We are rewriting. And you start with x1 equal to 1. What's happening? x2 is equal to 7 into 1 minus 18 minus 11. x3 will be 7x2 minus 18. That is minus 77 minus 18 minus 95. Then 7 into minus 95 minus 18 minus 683 and so on. So what's happening? Whether it is plus or minus, how it goes? It goes to infinity. In the negative direction, of course. Minus 11, minus 95, minus 683, minus 4,799, minus 33,611, and so on. So it is going towards infinity in the negative axis. So it diverges. There is no convergence. It is not coming close to a finite value, but it is keeping on increasing in its value, but that means it is divergent. Therefore, how you formulate the problem is very important. Of course, normally you will not be here asked to find any formulation of problem. Well, that is going to be an important part of your solving LPP, linear programming problem. First, you need to formulate the problem and then go about by various methods according to your syllabus. Of course, you will be starting with the simplex method and so on from next session onwards. That is going to form the second part of your title, linear algebra and optimization. With this, linear algebra will be over and then you will be taking up your optimization, that is operations research techniques, where you will be having this kind of formulation of problem. So in any problem solving, and you know very well, you might have come across in your day-to-day activities also, in your assignment also, in any domain you are working with, the formulation of problem is very important before you collect the data, analyze, use algorithms, and then go for finding result, and then of course come to your decision, etc. So if you take this way, what's happening? It is divergent. Okay. So you have to be, of course, in our problem, according to you, you will be asked to solve a given system of linear equations by direct method, that is by Gauss elimination. If no no insistence is there, by Gauss elimination. If there is an insistence, that by partial pivoting, that also to be taken care of. Coming to the indirect method, you have to be, if you are not given any uh, tag that you have to do by this method or that method, you are at liberty to use either Gauss-Seidel method or Gauss-Jacobi method. But in general, the question will carry the tag that solved by Gauss-Seidel method or Gauss-Jacobi method. Okay, right. But sometimes if there is enough time and the problem takes more marks in descriptive type, they may even ask by Gauss-Seidel method as well as Gauss-Jacobi method. So these are all various ways of putting the question. So extension to linear systems. So here we just have one equation, linear equation. It can be extended to linear systems, not by this way that we do it, but we solve Ax equal to B. Of course, we will be making use of the Quotient matrix and all those things you know very well. Of course, criteria for convergence. So one thing we are going to establish, the very concept of this criterion for convergence is norm R less than 1. This R is, you might have heard about correlation coefficient, sample correlation coefficient. Anyway, here we are not going to find any sample correlation coefficient, all those things. Here, what does that R stand for? That varies from case to case and for method to method, like a Gauss Seidel you have all. But anyway, you are going to see that whatever be the thing, the function for which you are taking norm is nothing but magnitude, isn't it? Norm is less than 1. Naturally, for convergence, norm R is less than 1. That R, what it is for Gauss Seidel method, what it is for Gauss Jacobi method, which they are going to be different to check for convergence. Okay, right. Now, and what is very important if you are going to start with, or in general, for both the iterative methods of Gauss Seidel and Gauss Jacobi, is that it should be, the coefficient matrix should be strictly diagonally dominant matrix. So here when it comes, when I use the word sufficient, you might have heard necessary and sufficient conditions. And when you write necessary and sufficient conditions, actually it means, when you write, you will be putting symbolically which means implies and implies, implied that, implies and being implied that. That means it is both ways, it is positive, it is possible. That is necessary and sufficient conditions. Whenever you might have proved in school days, might have in some theorems, both the cases, that means you will start with an assumption, you will end up with the proof. Conversely, that is a converse, but is also can also be proved. Conversely, whatever is proved will be assumed, and then you end up with the assumption. So it is called that. Some we will say that this leads to this and vice versa. BACE hyphen BERSA, vice versa means and conversely. So it is not always necessary that the converse is also true. Converse might be true. Converse may be true. Converse need not be true. So all these things you might have studied, you might have heard about. So whenever you talk about the conditions, it is not always, it need not be both necessary and sufficient. There are some conditions which are sufficient enough. For practical purpose, they are sufficient. They don't need to be necessary. They don't need to be mandatory. So like that, this condition we are going to see at the end of the session, that is not necessary. But it is sufficient to see that the principal diagonally dominant matrix means the absolute value of the principal diagonal elements, each of AJJ, A11, A22, etc., ANN. Suppose A is a matrix of n by n order. Absolute value of each of them must be greater than sum of absolute values of other elements in that row. In that way, the principal diagonal element is dominant, is greater than. Of course, why we say strictly means greater than, strictly greater than, not greater than or equal to, strictly greater than. That's why it's called a strictly. Okay. So this condition is sufficient and is important for both the iterative methods, that the coefficient matrix must be diagonally dominant matrix. If it is not the case, what will happen? We will see. And it is enough, that is, it is sufficient, but not necessary. Those things are also, we'll see just for understanding purpose at the end. Okay. As of now, it is enough to remember that the sufficient condition for both the iterative methods to exist is that it should be, the coefficient matrix must be diagonally dominant matrix. What do you mean by diagonally dominant matrix? Of course, strictly diagonally dominant. As or an n by n matrix A is called strictly diagonally dominant if the absolute value of each entry on the main diagonal is greater than the sum of the absolute values of the other entries in the same row wise. Okay. That's why sometimes they will even specifically say strictly diagonally row dominant matrix. Okay. Otherwise, it is understood that we consider row wise. Okay. That is, what does it mean? Modulus A11, first row. Principal diagonal element A11. So modulus A11 must be greater than sum of absolute values of other elements in that row. That is mod A12 plus mod A13 plus etc. plus mod A1n. Similarly, go to the second row. What is the principal diagonal element? A22. So modulus A22, only absolute values. That is very, very important. Must be greater than mod A21 plus mod A23 plus etc. plus mod A2n, etc. etc. You take modulus ANN. N rows, N columns, isn't it? So mod ANN is greater than mod AN1 plus mod AN2 plus etc. plus mod ANN minus 1. Okay. Now, with this understanding, this is the theorem. So this is going to be the sufficient condition which is to be checked. Which of the following systems of linear equations has a strictly diagonally dominant coefficient matrix? Can you just answer, Apur? So this is, so no, let me first complete. Therefore, when you put this symbol, it's a two-way traffic, both necessary and sufficient. Otherwise, it is only actually, as I just have mentioned, that this is only a sufficient condition. So sufficient condition means you can say it is a forward direction, implies that are being implied by either sufficient or okay, implies that are implied by or. So the anyway it is only one way sufficient condition. Okay, right. Right. Now, so can you just look at this and having understood the definition, can you tell me which are the following system of linear equations say strictly diagonally dominant coefficient matrix? Can you tell me?
The diagonal matrix is.
Look at the first one. First row, 3 is greater than mod minus 1. Isn't it? 3 is greater than 1. It's only 2 by 2. I mean, two equations into one ones. Second one, principal diagonal element is 5. See, what is the coefficient matrix here? See, the coefficient matrix is for the first problem, coefficient matrix is 3 minus 1, 2, 5. Isn't that? So 3 is greater than modulus minus 1. 5 is greater than 2. In the first row, this is the principal diagonal element which is greater than this. In the second row, 5 is the principal diagonal element which is greater than 2. Therefore, this is having a coefficient matrix 3 minus 1, 2, 5, which is strictly diagonally absent. Is diagonally dominant. Okay. Coming to the next one, 4, 2, modulus of minus 1. So 4 is greater than 2 plus 1. Fine. Coming to the second one, 0. So the coefficient matrix here is, for the second problem, you have 4, 2, minus 1, 1. There is no x term. 0 is the coefficient. And 2. Third row, 3, minus 5. So here, 4 is greater than 2 plus 1, 3. But 0 is less than 2 plus 1. And again, going to the third row, 1 is less than 5 plus 3. Isn't it? And remember, of the 3 rows, even if there is one row in which the principal diagonal element is less than, which is not greater than sum of the absolute values of the other two elements, it is not strictly diagonally dominant. So this matrix is not diagonally dominant. Is not diagonally dominant. Is it right? Is it clear?
Yes, sir.
Okay. It's very simple. Right. Now, of course, the same thing is given symbolically. The matrix A11, A12, etc., A1n, A02, N, A2, etc., A2, N, etc., AN1, AN2, etc., ANN is said to be strictly diagonally, as I just mentioned, row dominant if modulus of AII greater than summation of modulus of AIJ, J equal to 1 to N, J not equal to I. Okay, right. Now let's come to one of the two iterative methods by name Gauss-Seidel method. As I mentioned already, that the sufficient condition, look at the word, and that is enough, of course. It is enough. It is enough. We know, no, sometimes whenever you want to prove, it is enough that if you just prove this. So it is sufficient. So the sufficient condition for Gauss-Seidel method to solve a system of linear equations given by Ax equal to B is that coefficient matrix A is strictly diagonally dominant. So these are the things that will be useful to answer MCQs, maybe in quiz 2, if there is. Then the system is solved by solving the first equation for x1, the second equation for x2, and the third for x3, and so on, nth equation for xn. And what is very important here is latest values for the variables is used in each approximation. What is the meaning of this? So when you are given a system of linear equations, in practice normally maybe two equations in two unknowns, or at the most four equations in four unknowns, but more generally three equations in three unknowns. You will be writing x1 in terms of x2 and x3, x2 in terms of x1 and x3, x3 in terms of x1 and x2. Is it right? So that way you will be first rewriting after checking whether your coefficient matrix is strictly diagonally dominant matrix. Then we will be finding, we will have an initial approximation. Initial approximation, sometimes it will be given in the problem itself. By initial approximation, we don't always mean that it is 0, 0, 0. That means your approximation, initial approximation is nothing but initial assumption, initial guess. That means let x equal to y equal to z equal to 0. So that is called initial approximation. So unless otherwise stated, because in some problems they may say you start with the initial approximation x equal to y equal to z equal to 1. So that itself is the initial approximation. Okay. So it need not always be 0, 0, 0, but in general, unless otherwise you are asked to start with an initial approximation that x equal to y equal to z equal to 1, it is always considered to be x equal to y equal to z equal to 0 for the simple calculation. Is it right? So when you are putting x2 and x3 equal to 0 for finding x1, and that x1 value will be used in finding x2 and x3. So that the latest value for the, similarly for x2 and x3. So latest values for the variables is used in each approximation is the main component or version or important concept for Gauss-Seidel, which is not the case with the Gauss-Jacobi method. So this is where we have a distinction between Gauss-Seidel and Gauss-Jacobi method. What is the meaning exactly? You will see. That's it. You just write A11 x1 plus A1 x2 plus A1 x3 equal to B1. You have system of three linear equations in three unknowns. You know very well. So how do we write that? We have to ensure that mod A11 should be greater than mod A12 plus mod A13. Mod A22 must be greater than mod A21 plus mod A23. Mod A33 must be greater than mod A31 plus mod A32. In the sense, it is strictly diagonally dominant coefficient matrix. Once it is checked, we know very well, we can rewrite this as x1 in terms of x2 and x3. That is x1 equal to b1 minus a1 to x2 minus a1 3 x3 divided by a11. Similarly, x2 is b2 minus a21 x1 minus a23 x3 divided by a22. And x3 is equal to b3 minus a31 x1 minus a32 x2 divided by a33. Isn't that? So now we can start the solution process by choosing guesses by assuming for the x's, the values of x. A simple way to obtain initial guesses or initial assumption or initial approximation is to assume that they are all zeros. These zeros can be substituted into x1 so that first equation becomes x1 equal to b1 by a11 because x2 equal to 0, x3 equal to 0. So here don't put 0 equal to. Sir, you only said x1 equal to x2 equal to x3 equal to 0 is the initial approximation. Therefore, 0 equal to. It's not like that. When you are finding x1, you are substitute now for x2 and x3 to be 0. In the next equation, when you are finding x2, there is x1, b2 minus a21 x1. In that x1, you will have the latest value of x1, which you have found in the first equation. And x3 will be 0. And the third equation, your x1 is already found and x2 is just found. So that is how you have to understand. So in the right hand side only, your initial assumption values will be substituted as 0 for getting newer values of x1, x2, x3 as the case may be. See, this is what exactly is interpreted diagrammatically. First approximation. X1 you know very well, C1 minus A1 to X2 minus A1 to X3 by A11. And that is A11 that they have just taken it as some C1. So that X1 value is taken in the next equation. X2 equal to A1, what is that? A1 to A21. That is that just I mentioned C2 minus A21 X1 minus A23 X3 divided by A22. So the arrow mark shows, here. This value of x1 is taken here. This is what we mean by latest value of x1 is taken for finding x2. And having found x2, latest value of x2 is used here to find x3. Having found x3, latest value of x3 is used in finding x1 in the second approximation. And that value of x1 is used again for finding x2, and the value of x2 is used in finding x3 and so on. So this is how approximation after approximation we make use of the newer values of the variables in the subsequent calculations. Now, let's go for an example. Solve the following system of equations by Gauss-Seidel method. Generally, you will be given is a very important topic of solving a system of linear equations by iterative methods or by indirect method. To be precise, if you are given the method by which you need to solve, it will be given explicitly by Gauss-Seidel method or Gauss-Jacobi method. Okay, right. So you are given three equations in three unknowns, x1, x2, x3. First, look at the solution. First, you need to check whether the sufficient condition is met, is satisfied. What is the sufficient condition? So the coefficient matrix. What is the coefficient matrix here? I hope you will be able to visualize. First row, 3 minus 0.1, 0.2. Second row, 0.1, 7 minus 0.3. Third row, 0.3 minus 0.2, 10. Isn't it? Now, take the first row. What is the principal diagonal element? 3. What are the other two elements? Absolute values. Mod of minus 0.1 is 0.1. Another one is 0.2. So 0.3. 3 is greater than 0.3. And it should be true for every true row. That is important. Go to the second row, which is the principal diagonal element 7. What are the, yes? Yes, Ranjan? Hello?
Yeah, no issues.
Yeah. Yeah. Go second equation, principal diagonal element 7. You got to be careful about, isn't it? Which is greater than 0.1 plus 0.3. Go to the last equation. The principal diagonal element is 10, which is greater than 0.3 plus 0.2. So the coefficient matrix A, which is having the entries 3 minus 0.1, 0.2, 0.1, 7 minus 0.3, 0.3 minus 0.2, 10. 10 is a strictly diagonally dominant matrix. Okay, first thing that is to be checked. Then, by Gauss-Seidel method, the required approximation formulae are. So now we will rewrite the given three equations in terms of x1, x2, and x3. Because we are going to find in every approximation the values of x1, x2, x3 using this formula. It is just rewriting the given equation. That's all. X1 equal to 7.85 plus 0.18 x2 minus 0.2 x3 divided by 3 or 1 by 3 into x2 is equal to 1 by 7 into minus 19.3 minus 0.1 x1 plus 0.3 x3 and last equation x3 is equal to 1 by 10 into 71.4 minus 0.3 x1 plus 0.2 x2. So these are the three equations that are going to give you the approximations for x1, x2, x3 in every iteration. Okay. Now just look at the table like it is not necessary that you should only make tables like this. It will be useful to you. Okay. So iteration x1, x2, x3. Iteration 0. That means we don't do any iteration at all. We have not started it. So that of course we can say as a 0th iteration. Okay, x1 value 0, x2 value 0, x3 value 0. It's just for understanding purpose. Always normally we don't show initial 0th iteration. That means nothing is started yet except initialization. Now, first iteration. So you just go here, x2 0, x3 0. So you have 7.85 divided by 3. What is it equal to? 2.6167. 236, 1.8, 8.6, and then 5 divided by 3. So you have 1, 3, 20, then 6, 3, 18, then 27, 3, 21, 6, 6, 6, etc. So 2.6161. 6167. At that time, what is x2 then? Having found x1, x2 is 1 by 7 minus 19.3 minus 0.1 into, this is very, very important. In Gauss-Seidel method, latest value will be taken for computation of the next variable. So here don't put 0. Now x1 is found, and therefore that value of x1 is one you have to take. That is 2.6167. So minus 19.3 minus 0.1 into 2.6167. That is you have minus 0.2617. Okay. Plus 0.3 into this becomes 0. So you have only minus 19.3 minus 0.2617. If you add, you get minus, and that is minus, you get minus 19.3 minus 0.27 something. So you get minus 19.515 5 617, something like that, isn't it? So that you divide it by 7, you get minus 2.7945. Now go to x3. 1 by 10 into 71.4 minus x1 value you are already having 2.6167 plus 0.2 into x2 value you have recently found as minus 2.7945. You get 7.005610. Isn't that? So this is how you find set of values by using the latest values of the other variables. Second iteration. Now what will you do? One set of iterations is over. Next you are again finding x1. So now what will happen? 1 by 3 into 7.85 plus 0.1 into what is x2? Already x2 is there. This one only you have to use. Minus 2.7945 for x2. Minus 0.2 into, in the first approximation, you had x3 equal to 0. But now you have to take the latest value of x3, which is 7.00561. So if you calculate this, you will get now x1 value 2.990557. Using value of that value of x1, you get minus 2.499625 value of x2. Using x1 value and x3 is already there, the 7.005610. You get the latest value of x3 as 7.00029. Okay. According to this slide, according to the solution is, of course, it's not given as a final solution, but you can understand that we have stopped iterations and then given x1, x2, x3. So after 2 iterations, it is found that, well, I would suggest that you can go for one more iteration. You can go for one more iteration so that you will be able to find this 2.990557 will still be fine-tuned. I will be getting some 2.9999 something. And this will be minus 2 point, about maybe 49999 something. And this is, of course, 7.00. So that you can write the solution now. Therefore, finally, you should write the solution. That is very important. The solution is x1 is equal to 3. X2 is equal to minus 2.5. And x3 is equal to that's all. So this is the solution. Now you may have one doubt. Is it necessary that you need to round it off to 2.9999 to 3 at minus 2.49996 to minus 2.5 and x3 equal to 7.0? Of course, 7.000 you will get 7 minus 2.49. It's okay, fine. Better you can, nothing wrong in because after all it's approximation. So when you are writing the solution, you can give the better approximation by just rounding it off after doing about 2 or 3 iterations as the case may be, depending upon the requirement. So you just check as usual. Substitute the values of x1, x2, x3 in all of the 3 equations in the left hand side and see that it is equal to right hand side, whether they satisfy all the equations so that they become the solution. Okay. So you just see that. Take the first equation, 3 into 3, 9, minus 0.1 into minus 2.5. That is plus 0.25. Next is 0.2 into 7.14. So you have 9 plus 0.14. So you have minus, you just check. Just check. How? Can you just check quickly? 9 minus 0.1 minus 2.5. So it is becoming plus 0.25. And third one is 0.14. So you get, what do you get? X1, 9, 3x1, 9 minus 0.1 x2 0.2 plus 0.2 x3. X3 is 7. So you get 0.14. How much you are getting now? Are you getting the equation solved? Satisfied? You get everything positive, isn't it? 9.39 something.
It's positive, I think.
There is something. Just fine. Minus 2.5. Okay. So everything is positive. Okay. 3 into 3, 9. This equation is not satisfying. It's not satisfied. How is that? Is minus 2.499. Maybe that means that means this is not the solution then. I think it is still getting reduced. You see, look at here. This is of course going 2.6 to 2.9, and this is minus 2.79 to minus 2.4, and this of course is remaining the same.
Yeah.
It is 1.4, isn't that? So where is going wrong now? So you have 3x1, supposing x1 is 3, of course, suppose it is 3. 3 into 3, you have 9. Okay. Then 0.2 into 7. That is 1.4. Isn't that? So you have 10.4. So if you want to get 7.85, 7.85, you must get 10.4. You must get minus, you must get x2 value, x2 you must get positive value, isn't it? See, 9 is there, 3 into 3, 9. And 0.2 x3 is 1.4, not 0.14. 1.4, 0.2 into 7. So 1.4, that is you are having 10.4. Now to get 7.85, you must have minus 2.555. That is, you must have x2 as 2.55. Well, we have 2.5, but it is not minus. Can you just check quickly x2 equal to? Can you just quickly check from the equation x2 equal to? Apu,
Yeah. Do.
kindly check. Is it negative? 1 by 7 into minus 19.3 minus 0.1 into 2.6167 plus 0.3. Of course, that becomes 0. Everything is minus only. The next equation is satisfied. It is coming correctly. So the answer is right. What is happening to the first equation then? Okay, anyway, just check. Look at the second equation. It's coming correct. See, you have 0.1 into x1, 0.1 into 3, it is 0.3, plus 7 into x2, that is 7 into minus 2.5, that is minus 17.5. Is it right? Minus 0.3 into 3. Minus point, I mean, my 0.3 into 7, that is 2.1. So minus 17.5 minus 2.1, you get minus 19.6 plus 0.3 minus 19.3. That is right. Right hand side is correct. Second equation is satisfied. How about the third one? How about the third one? 0.3 into x1. That is point 0.9. 0.2 into x2. That is 0.2 into plus, that is 0.5. And next is 10x3, 70. Yeah, that is also correct. Look at 71.4. Second equation, third equation, they are satisfied. What about the first one? First one, 3 into 3, 9. 0.1 into x2. Anyway, you just check. Okay. I have checked the second and third equations are correct, satisfied. If they just check the first one. So you can just go for one more approximation and then come to the conclusion. I think that would be better. So I just remove this. You can cross check and then find out if you want, you can go for one more iteration. Second and third equations I have seen now. They are all satisfied with this x1 equal to 3, x1 equal to minus, x2 equal to minus 2.5, and x3 equal to 7. Why it's not the case with first one? Please check. Okay. Right. I will also check in the meantime. Next. Solve the set of equations by Gauss-Seidel iteration starting from 0, 0, 0. So of course, here are 4 equations in 4 unknowns, starting from 0, 0, 0. So it is given in the question itself that you don't need to assume on your own. It is given in the question itself. Therefore, the initial approximation, that is at the 0th iteration, x1, x2, x3, x3, x4 equal to each equal to be assumed as 0. Of course, we rewrite the equations like this. That is because you are dividing by 10. And before that, you have to check for strictly diagonally dominant matrix is your coefficient matrix. That is to be checked. So it is 10, which is greater than 2 plus 1 plus 1. Take absolute values. Then 10 is greater than 2 plus 1 plus 1. Next, it is greater than 10 greater than 1 plus 1 plus 2. Well, again, 10 greater than 1 plus 1 plus 1, 2. Therefore, it is a strictly diagonally dominant matrix is your coefficient matrix. So you can now rewrite the equations to have the formula x1 equal to, so you have divided by 10, therefore you have 3 divided by 10.3, and then you have of course 2 plus 0.2 x2 plus 0.1 x1 plus 0.1, 0.1 x3 plus 0.1 x4. Similarly, here everything they have already divided by 10, so they have made it in terms as a real number. So it's the same kind. Well, here the table is readily available. Better you put your hands to practice to find out those values substituted there. So first iteration, n here stands for number of iterations. First iteration, x1 equal to 0.3, x2 equal to 1.56, x3 2.886, and x4 minus 0.1368. Okay, so just to have a glimpse of what it is done, you just see that during the first approximation, x2 0, x3 0, x4 0. So x1 is just 0.3. So it is given there, x1 value 0.3, x2 value 1.56. Just to have an idea, let's just go back. 1.5, x3 0, x4 0, but x1 value is recently found. What is that? 0.3, isn't it? So 0.2 into 0.3, it is 0.06. So 1.5 plus 0.06, 1.56. Just look at 1.56. Okay. So when you go to x3, when you go to, sorry, x3, you have 2.7 plus 0.1 into 0.3, that is 0.03, plus 0.1 into your x2 now, isn't it? That is, you have 2.7 plus 0.1 into x1, that is 0.03 now, plus 0.1 into x2, that is, you have already you have 1.56, so it becomes now 1.56, 0.156, and x4 will be 0 now. So if you add these three, you get 2.866. You should get x3 value 2.866. Correct. Go to x4 now. x4, you have minus 0.9, 0.1 x1, that is 0.03, then 0.1 x2, that is 0.156, and x3 value 2.866, 0.2 into. So you have 2.886 into 0.2. 0.5772. Okay. So if you add, you get these three addition. Point 0.7632 minus 0.9 plus 0.7632. You get minus 0.1368. Yes, minus 0.1368. So similarly, you go for second iteration, third iteration, fourth iteration. Why you are going? Number of approximations or number of iterations you need to go is not restricted in your question. So you need to fine tune. You have to go for better approximation by doing iteration after iteration until you reach at least until you reach two iterations where you get almost the same values are there converging to almost the same. You just see here, for example, you are proceeding like this and you want to know, since it is not given where you have to stop, you just see that 0.3, 0.8. So you need to go further. 0.98, you need to go further. 0.99. It is given fifth iteration 0.994. Similarly for x2, 1.562 quantum jump, 1.95, then 1.98. Then of course it is coming closer, converging 1.998 to 1.997. And similarly here 2.8866, 2.95, 2.99, 2.9987, 2.998. And then here of course minus 0.13, 0.02, 0.00, 0.00, 0.00. So the more the approximations, greater the better results, better approximation. So at least, of course, because it it is time consuming. So you can at least stop with the fifth iteration, and then you can still say that it is 0.999 or 1 itself, 1.999 or 2 itself, 2.999 or 3 itself, minus 0.000, so it is 0 itself, no mention of 0. So you can now, as I just mentioned in the beginning, that you can always give the round of value, having found two of the iterations to give almost near the same values. So here having found, since here it is gone up to fifth and sixth iterations, where you will see very close approximations, very close. Only in the fourth decimal place there is a slight change. Otherwise you can go about. So you can now declare that the solution is x1 equal to 1, x2 equal to 2, and x3 equal to 3, x4 equal to 0, which you can check always. Just see here, 10 into 1, 2, 3, isn't it? So 10 into 1 minus 2 into 2, 10 minus 4, 6, minus 3. 6 minus 3 minus 0. So you get 3. Similarly, you can check for other three equations also. Okay. But it's already 5:26. Shall we have a break and then continue? Apurranjan?
Sure, sir.
Okay, okay. Shall we resume? Hello?
Yes, sir.
Okay, good. You see. Given the system, very well Ax equal to B and starting values, see just a notation. You are putting X, some set builder notation and superfix 0. It's nothing but you don't need to go for about set builder notation, all those things. Sometimes some authors used to have superfix 0, 1, 2 to mean zeroth approximation, first iteration, second iteration, etc. That's all. It's just a notation. Okay. So starting value means x1, x2, x3. Supposing there are three unknowns, 0, 0, 0. That's the meaning. Gauss-Seidel uses the first equation to solve the first and second, first, second, and so on. Okay. So that's what is given. We know very well. X1 equal to B1 minus A1 to X2 minus etc. All those things we know very well. Okay. Now, what is written here? How long you go for the approximation, that we practically know, that we stop doing iteration the moment we see the two such iterations values are so close to each other, so that we can stop iteration. Or supposing the problem really goes up to 6 or 7 iterations, there are occasions like that, and that the question, if it is just for 4 or 5 marks, or if the time management, due to time management, the question is, in the question it is given that do approximation up to third, up to fourth, you have to stop. Okay. So, but anyway, so what is in general the condition? After the first iteration, you get x super 1, use these values to start a new iteration, and so on. Repeat until the tolerance is satisfied as. Here the tolerance is nothing but the condition. Okay. What is the condition? And don't bother about all those that use notations, modulus epsilon a comma I, etc. You just look at the right hand side. Modulus xi, that is values of x1, x2, x3, superfix k, that is after kth iteration, minus, for example, x1 after third x1 superfix 3 minus x1 superfix 2, that is values of the unknowns after the kth iteration minus their values during the previous iteration, that is k into iteration, divided by the kth iteration value again, modulus. That is, this is actually called the difference between the latest and its previous by the original, the, that particular iteration. If it is into 100%, that is, it is less than 100% means again by 100 by 100. So anyway, that marginal value is less than epsilon. Epsilon means it is a very, 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 very small quantity tending towards zero. So if it is less than epsilon, it is a very, very small quantity tending towards zero. Less than epsilon means actually tending towards zero. So in practice, you will get very small quantity like 0.00001, something like that. For all the unknowns, I equal 1 to n, where k and k minus represent the present and the previous iteration, then you are repeating the CETs. In practice, if you just look at without bothering about all these notations and conditions like this, it is to be put, and you will not be asked to write this condition. What does it mean? You need to do the repetition of iterations until you reach the iterations may be present and the previous one to be very close to each other. That's the crux of the problem. That is the idea behind this. Okay, so don't bother about all those notations, etc. Now, look at just with that notation. Here is a problem. Same idea, same thing. Solve the following system of equations using the Gauss-Seidel method. 6x1 minus 2x2 plus x3 equal to 11, minus 2x1 plus 7x2 plus 2x1 equal to 5, x1 plus 2x2 minus 5x3 equal to minus 1, starting with, it is given in the question itself, x1 superfix 0 equal to x2 superfix 0 equal to x3 superfix 0 equal to 0.0, means the initial approximation is started with x1 equal to x3 equal to x1 equal to x2 equal to x3 equal to 0. That's just given as a real number 0.0, because you will be ending up with decimal points, etc. in all your problems. You don't need to approximate it in the beginning itself. You go iteration after iteration and then see after some number of iterations that they are close to each other. That's the meaning. Okay. So for before that, you have to first check whether the coefficient matrix is diagonally dominant. Of course, that you can write it here. I would suggest better you can. Before you start, rearrange the equations to get the formulae for x1, x2, x3 in terms of the other variables, and then go for iterations in that order. I would suggest to you that you write here solution, that is here you can write solution starts. For that, first you ensure that this is a solution. The coefficient matrix is, I just write, instead of writing in full, diagonally dominant. There is no such reserved abbreviation. I just use, for simplicity, is DD, diagonally dominant. Why? If you look at the first row here, 6 is because I can write the reason for or means because in the first row, 6 is greater than modulus of -2 plus modulus of 1, that is 3. In the second row, 7, the principal diagonal element in that row, is greater than modulus of -2, 2 plus 2, 4. And in the third row, 5 minus 5 actually is the coefficient of x3. So you have to take modulus of it, which means 5 is greater than 1 plus 2, 3. That's the reason why it is given strictly. It's not greater than or equal to, it should be strictly greater than. So in the first row, principal diagonal element 6 is greater than modulus of -2 plus modulus of 1. That is 2 plus 1, 3. In the second row, 7 is greater than modulus of -2 plus 2. That is 2 plus 2, 4. And in the third row, modulus of -5, absolute value, 5 is greater than. If you don't take absolute value, what will happen? 1 plus 2, 3 is greater than -5. So isn't it? That will go in the opposite direction. That means it will go in the opposite sense, which is not correct. Therefore, you have to take absolute value of the principal diagonal, which is 5, which is greater than 1 plus 2, 3. Therefore, it is strictly diagonally dominant coefficient matrix as usual. Therefore, x1 can be written as 11 plus 2x2 minus x3 divided by 6. x2 5 plus 2x1 minus 2x3 divided by 7. x3 is equal to -1. Is it -1 or +1? I think it should be 1, it seems. Everywhere it is given only 1. So in the question also it should be 1, it seems. Maybe better you check because everywhere it is given only 1. Here also it is 1, 1, so it should be 1. It seems plus 1. Okay, so x3 is 1. Oh, it is minus 1 only. So they have removed the sign. Okay, okay, okay. But they have multiplied throughout by minus, it seems. Okay, okay. So it is minus 1 only here. Yeah, that's right. That's why they have changed it now. Minus x1 minus 2x2 plus 5x3 becomes plus 1. So that it is now 1 minus x1 becomes plus x1 and minus 2x2 becomes plus 2x2. That's right. So it is now minus 5 become plus 5. So they have made the coefficient of the concerned variable to be positive. Okay, that's right. This question is actually, it is only minus 1. That's right. Right, right. Okay. So x1 0, x2 0, x3 0 is 0. Therefore, first iteration x1 superfix 1, that is 11 plus 2 into x2 superfix 0 means initial value, zeroth iteration value, minus x3 superfix 0. Superfix notation is no used, divided by 6. That is 11 plus 2 into 0 minus 0, you by divided by 6, you get 1.833. Similarly, x2 superfix 1, x3 superfix 1, right? And then, so here you have used, see here, 5 plus 2 into latest value of x1, 1.833, which we have found here, minus x3 value, of course, 0 initially, divided by 7. So when you are finding x3, you are getting 1 plus x1 value, latest value 1.833 plus 2 into x2 value, we just have found out 1.2381. Okay, so you get 1.062. So like that, you go for second iteration and so on. Well, so here it is, check. Always check the convergence using specified tolerance. Specified tolerance in the sense, practically speaking, simply speaking, you go up to the number of iterations where at least two of them to be coinciding with each other almost. So 0th, first, second, third, fourth, fifth. It is gone up to fifth. So 0th means x1, x2, x3, 0 each. So first, since it is every here every value is having 3 decimal places, here also it is just given in the same fashion, 0.000. Otherwise, if you just put 0 also, nothing wrong. So 1.833 we have seen, 2.069, 1.998, 1.999. Of course, from this itself we can, you can see here itself third and fourth, but still if you go further, you are able to see the very better approximation, the best approximation rather, 1.999 becomes straight away 2 and 1.000, of course 1.000, 1.0. So the values of x1, x2 and x3 are 2, 1 and 1. Okay. Just check now. 6 into 2, 12, minus 2, 10, plus 1, 11. Minus 2 into 2, minus 4, plus 7, 3, plus 2, 5. Now look at this. 2 plus 2, 4, minus 5, you get minus 1. So the solution is x1 equal to 2, x2 equal to 1, and x3 equal to 1. Do you have any difficulty in understanding this? Do you have any question to ask? Anything you want to seek any clarification? Apu?
Fine, sir.
Okay, fine. Right. Now, convergence and matrix norms. So already we have seen this matrix norm in terms of which we call it as our corresponding to vector 1 norm, vector infinity norm, and vector 2 norm or Frobenius norm. We are already familiar with in the last but one session itself, but still we can, because it is going to be useful to get the convergence norm found, whereby we can declare that the system of equations is convergent for Gauss-Seidel method or Gauss-Jacobi method, which of course has different conditions. Some of the commonly used matrix norms are given below because matrix norm corresponds to the vector norm. Anyway, here we are interested in matrix norm straight away because we are going to talk about matrix norm. That is the norm for A, where A is the coefficient matrix, which is playing the significant role. Matrix norm corresponding to vector 1 norm is maximum absolute column sum. Maximum of sum of absolute values of column elements. That's the meaning. In short, it is given maximum absolute column sum. That is norm A suffix 1 equal to maximum of sigma modulus Aij. I varies from 1 to n, maximum J. Okay, over J. Similarly, matrix norm corresponding to vector infinity norm is maximum absolute row sum. That is maximum of the sum of absolute values of each row. That is norm A suffix infinity is maximum summation of modulus A j equal to 1 to n summation maximum of I. That is over row, isn't it? Next, norm A suffix 2 is also called Frobenius norm. And so it is called norm A suffix. It is denoted as norm A suffix 2 or norm A suffix capital F at times. Okay, that is square root of summation double sigma, that is double series, modulus Aij square, which means you take sum of squares of all elements, row wise as well as column wise. But don't duplicate. Either you go by rows or by columns. Take all those elements. Just a minute, I will just plug in the power. So you will take absolute value of each of those entries, square them, take the sum of squares of absolute values of all the entries. Better you can take that way. Row wise, column wise, double sigma means row wise as well as then column wise. Instead, you can simply remember this way, square root of inside what is that? Square of sum of squares of absolute values of all the entries. Okay, that is your norm f suffix 2 or norm a suffix f. Frobenius or 2 vector 2 norm. Okay, right. Where we are going to use this norm a suffix f, that is Frobenius norm, where we are going to use a norm a suffix infinity. Okay, right. Now, to get the condition for convergence, for Gauss-Seidel, we have one, and for Gauss-Jacobi, we have another condition. What is that? Consider the system Ax equal to B, system of linear equations. Write A as I plus L plus U. Already you are familiar with the decomposition of the given matrix into lower and upper with different conditions over there. That is done by three different methods called the Doolittle's method, Kraut's method, and Cholesky's method. There the idea is different. Okay. What exactly? Of course, L stands for lower triangular, U stands for upper triangular, but there we had some different conditions for different methods. But here we have the decomposition I plus L plus U, where we are going to have a simple way of representing them. I, we know very well, identity matrix. L is the lower triangular matrix. That means entries above the principal diagonal elements are zeros. Isn't it? And also, we consider here principal diagonal elements also zero. That is how we are doing the decomposition here. U is upper triangular matrix, and you know very well, entries below the principal principal elements are zeros. Not only that, diagonal entries are also to be taken as zeros. So in such a manner, if you write L and U only, then your matrix, coefficient matrix will be equal to, isn't it? So here, the decomposition, we are not doing by any different ideologies. In Doolittle's method, you are taking, you are giving importance to lower triangular matrix so that upper portion becomes zero. Not only that, and principal diagonal entries each should be equal to 1. And for U in cross, U will be as it is. And for Kraut's method, you are giving importance to upper triangular matrix so that you have principal diagonal element is each equal to 1. That condition is also there, apart from upper portion existing. Lower elements are zeros. L is L as usual. And of course, in um, Cholesky's method, it is your U is L transpose. L transpose. So LU will become L transpose. Transpose of the lower, isn't it? And therefore, there you are having the product LU decomposition. Here we are writing sum of. So if you just add this I, this type of L, as usual, lower triangular is lower triangular, but also principal diagonal entries are zeros. Similarly, U is upper triangular matrix, but also diagonal entries should be 0. Then if you add them, it is actually you are only writing them as sum of these three matrices. It's not exactly, you cannot say it is decomposed into the way that we have done already. So that is different. So it is just you are ensuring that you are able to express your coefficient matrix A as sum of these three matrices when you are writing I, of course, identity matrix, L in this fashion, U in this fashion. Okay, right. Then AX will be I plus L plus U into X equal to B. So what will happen x power k plus 1, that is k, x, it's not x power k plus 1, the x value at the k plus 1th iteration. Minus L x power k, minus big L comes this side because you have the right hand side you have k, x superfix k. So minus L x power k minus U x power k. And what will happen to Ix? Ix is x only, isn't it? So plus B, which is already there. And this is the case for cos Jacobi to get the approximation value. But anyway, in practice, you will be able to do as we have done so far. For Gauss Seidel, same way you will be doing for Gauss Jacobi. So there you don't need to follow this formula. As usual, you can do your iterations. Gauss Seidel you go see, Gauss Jacobi you are going to see. It's also almost similar, but with a slight difference. Okay, the next superfix k plus 1, that is values of x after the k plus 1 iteration is minus of I plus L inverse into U minus of I plus L inverse into U. Of course, value of x at the kth operation, kth iteration plus I plus L inverse into B Gauss Seidel. Anyway, you are not going to exactly put this formula for finding your iterations. You can do it the way that we have done so far. Okay, but this is what exactly the formula, okay, which you don't need to worry about to substitute. You will be able to find as usual what we have done practically. Okay, so from this, it is going to give you an idea that the condition to be satisfied for convergence, sufficient condition here again. Okay, sufficient condition is sufficient. Okay, don't bother about necessary and sufficient condition. So sufficient condition is for Gauss Seidel, sufficient condition for convergence. Sufficient condition for using Gauss Seidel is your coefficient matrix to be strictly diagonally dominant matrix. Same is the case with the Gauss Jacobi also. That is for proceeding with the method. But this method, this condition is actually for convergence condition for Gauss Seidel method. That is norm of this portion only. When you take norm of, you don't need to bother about minus, isn't it? Because minus of I plus L inverse, when you take norm, it becomes I plus L inverse into U, isn't it? Because norm of minus means it is modulus of minus 1, which is plus 1. So norm of I plus L inverse U should be less than 1. So for any convergence, you know very well, there are of course a lot of tests for convergence. Might have studied in school days in under sequences and series, convergence and divergence. So here also you can easily remember that way. Norm of I plus L in I plus L inverse into U is less than 1. Okay. For Gauss-Seidel convergence. For Gauss-Jacobi, we are going to see so. Okay. So in general, that this is actually rho. Rho is actually something like your R. Modulus of that portion or norm of that portion will be less than 1. What is that? In fact, instead of this, we are going to in fact check your matrix norm with respect to infinity, or that vector 1 norm or vector infinity norm or vector 2 norm. Here we are going to see in practice. Okay. So don't much bother about that. Now, test of convergence of the Gauss-Seidel iteration. Okay. So here you don't need to solve the system of linear equations given by iteration after iteration or by iterations or by iterative methods. It's enough. You check the sufficient condition for convergence of the Gauss-Seidel iteration method. What is that? We just have seen now. For Gauss-Seidel, minus of, that is norm of I plus L, norm of I plus L inverse, that is inverse of some of these two matrices into U. Okay, you have inverse of sum of two matrices is a matrix. And U is another perpendicular matrix. If is your A is a matrix of order 3 by 3, inverse of I plus L will be 3 by 3, multiplied by U of order 3 by 3, you get a matrix of order 3 by 3. And what is its norm? Which norm you will be finding? That is important. When you are finding norm, whether suffix 1, suffix infinity, suffix 2. That is important, isn't it? That we will see now. Okay, right. So for Gauss-Seidel test of convergence. So come to here. It is given norm C. What is C? Just for simplicity, minus of I plus L inverse U. You can just represent by a simple notation, a single letter, C. Letter C. Let us take C equal to this much. Okay. So we compute the Frobenius norm of C. So we have written here in the previous one, norm of I plus L inverse U or norm of minus of I plus L inverse U. It doesn't make any difference. It should be less than 1. But norm suffix what? 1 or infinity or 2. It is 2. For Gauss-Seidel test for convergence of Gauss-Seidel iterative method is norm minus of I plus L inverse into U suffix 2 or suffix F Frobenius. Okay, right. Should be less than 1. Let's see. Test whether Gauss-Seidel iteration converges for the system. So this is the question. So you have to be careful about the question. Don't immediately jump to the conclusion that you go for iteration after iteration. Test whether the Gauss-Seidel iteration converges. It's something like whether that system is consistent. You are not asked to find the solution. If it is, find whether it is having unique solution. If so, find the solution itself. If it is having unique infinitely many solutions, find them. If it is inconsistent, you will write no solution, isn't it? Something like that. You need to only test it, whether the Gauss-Seidel iteration converges for the system. That means definitely it will brook the solution. But here you are not asked to solve and get the solution. Test the convergence, okay, for the Gauss-Seidel iteration method for the system given. Okay, right. So here, of course, you don't need to. You can also automatically you can check, but you don't need to show that the coefficient matrix is diagonally dominant. All those things. It is automatically understood. Okay, because when you are going to test the convergence, that itself shows that your system is consistent for brooking the solution, giving you the solution. Okay, therefore you don't need to check. Even if you check, nothing wrong in it. 2 is greater than. Here, of course, it is 1 plus 1. So you look at here. So it is given actually here greater than or equal to, but anyway, don't bother. We are going to only test for convergence. Okay. So the decomposition is here it is given inside multiply the matrix by half. And it's given a question. There is a question why. Why we are multiplying by half in order to make the principal diagonal elements to be one each. Suppose you are having 3x plus y plus z, then x plus 3y plus z, then x plus y plus 3z, you will dividing throughout by 3 because you need to have in the principal diagonal it is to be 1, 1, 1. Then only, why it is 1, 1, 1? Because you are going to have the given A written as sum of three matrices, namely I, L, U. Isn't it? That I is 1, 0, 0, 0, 1, 0, 0, 0, 1 because it's a 3 by 3 matrix. So you need to have 1. That's the reason why you multiply the matrix row by half. Okay. So you have the matrix of coefficient, that is coefficient matrix to be, first you write, that is what we are interested in, isn't it? A. 1, 1 by 2, 1 by 2. We are not going to solve. We are not interested in Ax equal to B. We are interested only in A. And write it's a decomposition. Decomposition in the sense, sum of the three matrices. 1, 1 by 2, 1 by 2, 1 by 2. Here it is 1, 1 by 2, 1, 1, 1. Sorry, half, half, 1. So this you are writing it as I plus L plus U is equal to I. You better you write 1, 0, 0, 0, 1, 0, 0, 0, 1. Then it will be easy for you to understand. Plus, now you just look at L, lower triangular matrix means you will have elements only in the lower part of the matrix that is below the principal diagonal elements. So you will write half, half, half. And what is the main condition? Principal diagonal entries should all be zeros. Okay, zeros. And you know very well this triangular portion will also be 0, isn't it? Because it is lower triangular matrix. Same way, when you go to upper triangular matrix, only above the principal diagonal entries you will have the entries. That is half, half, half. This triangle. And lower triangle, you will have 0, 0, 0. Apart from it, all your principal diagonal entries must be 0 each. Right? Now you can check. I is 1, 0, 0 first row. You just add now 1 plus 0, 0 plus half, then 0 plus half. So you get 1 half half. Second, 0 plus 0, half. 0, you had 1 plus 0 plus 0, 1. Then you have 0. There you had 0, 0, half. You have half. And then half, you had 0 there in I plus 0, 0 plus half plus 0, you have half. Then you had 0. So 0 plus half plus 0 is again half. Then you had 1, 1 plus 0 plus 0, 1. So it is always possible to write your A in this fashion because we need to find the product of inverse of I plus L and U. For that reason, we are writing. Okay, right. So let us say C equal to, we straight away go to this. Now, I is 1, 0, 0, 0, 1, 0, 0, 0, 1 plus L is this one. Okay, now find out I plus L. Of course, I have done for you, but I cannot write now. It takes time. So you can just understand easily. I plus L is nothing but 1, 0, 0 minus I is outside, of course. 1, 0, 0 minus half 1, 0 minus 1 by 4 minus 1 by 2, 1. Isn't that? So that I have found out. How did you find inverse? What is I plus L? I plus L is actually 1, 0, 0, 0, 1, 0, 0, 0, 1 plus 0, 0, 0, half 0, 0, half, half 0. That is 1, 0, 0, half 1, 0, half, half 1. Okay. That is your matrix. Then let the matrix be some letter B. Okay. Now you find B inverse. Isn't it? B, I plus L inverse. How will you find B inverse? Easy way. 1 by determinant B into adjoint B. Find the matrix of cofactors. Take its transpose. That will give you adjoint. So adjoint A, I have found adjoint matrix 1, 0, 0 minus half 1, 0 minus 1 by 4 minus 1 by 2, 1. Therefore, C is now So that is inverse matrix. Determinant B is 1. You can easily find. So I have straight away found B inverse as 1, 0, 0, minus 1 by 2, 1, 0, minus 1 by 4, minus 1 by 2, 1. So you should be able to find inverse of the matrix by your usual easy method. You know how to find. Gauss-Jordan method, if you are asked to find in that particular topic, you are supposed to do only by Gauss-Jordan method. Otherwise, which you basically, whenever you are doing it for the purpose of using it, here you can easily find 1 by determinant A into adjoint A gives you A inverse. That formula you can find. So I have found inverse to be minus 1 minus I have taken inside minus of IL plus I plus L, that is some capital B inverse as minus 1, 0, 0. Then, of course, here it is given minus I have taken inside. So this portion will become, I also found out minus of B inverse is 1, 0, 0, minus 1, 0, 0, half minus 1, 0, 1 by 4, 1 by 2, minus 1 into U. U is already there. So the product is already shown here. Now, this is your C, for which you take the num. Which num you need to take? Suffix 2. Suffix F, Frobenius. That means square root of. So that's what is given here as power 1 by 2. So sum of all elements, square of absolute square. If you find square, of course, you don't need to worry about absolute value. Square of all the elements. Okay, row after row or column after column. That means all the elements you are taking into account. 0 plus 1 by 4 plus 1 by 4. Okay, plus 1 by 16 plus 1 by 16 plus 1 by 64 plus 9 by 64. See, look at it is 50 by 64 power 1 by 2. That is square root of, you get 0.884. Square root of 50 by 64 is root of 25 into 2 by 8 into 8 or 5 root 2 by 8. So 5 into 1.414 by 8 gives you 7.070 by 8, which is 0.884, which is less than 1. So norm C suffix capital F or suffix 2 we can put. Here I would suggest to you. So we are putting suffix 2. Yes, less than 1. Therefore, we conclude that this Gauss-Seidel iteration converges. This Gauss-Seidel iteration. Okay. Now, there is a footnote. It is interesting that the other two norms would permit no conclusion, as you should verify. Of course, this points to the fact that 8 means this is the number. Of course, it is given in the maybe the book from where it is pasted, is sufficient for convergence rather than necessary. It is enough. Okay. So what is the other two norms? What is the meaning? Norm C suffix 1. That is maximum of column sums, isn't it? I get maximum of, you can check. This is sum is 0. This sum is 7 by 8. And this sum is 9 by 8, which is maximum 9 by 8, which is greater than 1. Okay. And if you take norm C suffix infinity, maximum of row sum, that is maximum of I get 1 comma half comma. Here I get 1, here I get half, here I get half. So what is maximum? 1. So it should not be 1. It should not be greater than 1. It should strictly be less than 1. So other two norms gives no conclusions. And it is good that norm C suffix 2 is less than 1. That is right. So just by finding norm C 1, norm C infinity greater than 1, you should not say that it is not convergent. Okay. So it is sufficient to see that it is norm C suffix 2, that is Frobenius norm, is less than 1. So this is convergent. Okay. Gauss-Jacobi method. Okay. So I just go quickly. Can I just wait for another 5 minutes, 5-10 minutes, so that I will complete this? Apur?
Sure, sir, sure.
Okay, no problem. It's going to be easy. Gauss-Jacobi method, two assumptions made on Jacobi method. The system given by has a unique solution. Of course, it is the very common that need not be tested because system must be consistent and it has a unique solution. That is a condition for your Gauss-Seidel also. But What is important is the coefficient matrix A has no zeros on its main diagonal, namely A11, A22, etc. ANN are non-zeros. So this is not the condition for your Gauss seidel. Instead, you had another condition, sufficient condition to check it is strictly dominant coefficient matrix. But here, you must definitely have this condition that the principal diagonal element should only be non-zeros. Okay, right. If any, suppose, if any of the diagonal entries A11, A22, Xn are 0, then rows or columns must be interchanged to obtain a coefficient matrix that has a non-zero entries on the main diagonal. So you can interchange rows or columns so that the principal diagonal entry should only be non-zero entries. Is very, very important condition to be met for Gauss-Jacobi method to give to get to be solved. Now, what is in what way it is different from your Gauss seidel? If you come to know that, that is all other things are the same. You just see that. Gauss seidel always uses the newest available value x values, latest. Jacobi method uses x values from the previous iteration. What's the meaning? Just look at it. Repeat the previous example using the Jacobi method. So already we had a problem. I hope you would be able to just recollect. Here we just have seen, not this one. See this problem. You can easily understand this, rearranging the solution. Okay, well, so x1 equal to divided by 6, divided by 7, divided by 5. Kindly remember this, okay? We are taking up the same problem for doing now by Gauss-Jacobi method. In what way it is going to be different, you just check. Now, so this is the same. The example using repeat the previous example using the Gauss-Jacobi method means the problem that we have done just now using Gauss-Seidel method is taken. So instead of writing the question again, it's given like that. So we have now taken up. Hope you understood now. Now what we are doing, as usual, first iteration, use x super not values. Nothing is given, x super not values. In that problem, it was given to take 0.00. Whether it is given or not, if it is given other than 0, you have to take 111, something like that. If it is not given, it is always assumed to be 000. So you just see x1 superfix 1 first iteration 11 plus 2 into x2 superfix 0 minus x3 superfix 0 divided by 6. Same formula. 11 plus 0 minus 0 divided by 6, 1.833. If you are able to recollect, you just see that it was 1.833. Okay. Okay. Up to this, okay. Go to the next. X2 superfix 1, first iteration, x2 value. 5 plus 2 into x1 power 0. I mean, x1 superfix 0 minus 2 into x3 superfix 0 divided by 7. 5. Look at this. Look at this. What would you do? What you have done in Gauss-Seidel method? Ranjan, are you able to understand? Are you able to see the difference? Here, the formula you would not have written here, x1 superfix 0. For x3, you will write superfix 0, initial value. But you would have written here 1 because x1 value is just found. The latest value of x1, that is x1 value after first approximation or first iteration, will be taken up here as 1.833 in your Gauss-Seidel method. Whereas in Gauss-Jacobi method, you need to take in the very first iteration only initial values of x, 0, 0, 0. That is the difference between Gauss-Seidel and Gauss-Jacobi. Only after completing a set of iterations, you have to go for the latest value. In the latest in the sense, for example, see here, see, it is not 1.833 but 0. Well, this is 0, you get 0.714. Next, 1 plus, again, look at this. It is not given x1 superfix 1, the same x1 superfix 0. So it is 0, 0, x2. Again, look at. In Gauss-Seidel, you would have got x2 superfix 1 here because x2 value is just found. Of course, that would have been different here because of this value will be different, and this value will be taken here. So you will get correspondingly a new x3. Isn't that? So in Gauss-Jacobi method, in the first iteration, you will have for all the three variables only initial values of x1, x2, x3. Whereas in Gauss-Seidel, in finding x2, you will take the latest value of x1. In finding x3, you will take the latest value of x2 as well as already existing x1. So that these are a different set of values in your first iteration for the same problem. Then you may ask one question. If this is the way it is going to change, will there be a change in the solution? No. Equations are the same. You are going to get the same 2-on-1 solution. But the iterations procedure will be different so that you will be ending up with the same solution after a good number of iterations. Let's look at,
Okay.
try to remember 1.833, 0.714, 0.2 after the first iteration. Just go back there. After the first iteration, 1.833, okay, 1.238, 1.062. Isn't that? So this is how the change is occurring. That's all. Second iteration, use x super 1 values. Now you need to supply the values of x1, x2, x3 during the what you have obtained during the first iteration, namely 1.833, 0.714, 0.200 in all your calculation for x1, x2, x3 value during the second iteration. That is, you just look at here. Look at here. X2 superfix 0, x3 superfix 0. X1 superfix 0, x3 superfix 0. X1 superfix 0, x2 superfix 0. When you want to find 1, 1, 1. So when you want to find second iteration, during second iteration values of x1, x2, x3, it is all going to be x2, x3 superfix 1. X1, x3 superfix 1. X1, x2 superfix 1. That is, you will put 0.714 for x2. 0.2 for x3. 1.833 for x1, 0.2 for x3, 1.833 for x1, 0.714 for x2. So you get new set of values during second iteration. Like that it is proceeding. Okay. So finally, maybe after doing a good number of iterations, you will end up with the same way. Okay. Right. So you will get the same kind of solution after a good number of iterations, maybe 6 or 7 or iterations, 2, 1, 1. That was the solution I remember. Now, convergence of Jacobi method. Here, you had C equal to, that is just a notation, just to remember, C equal to minus of I plus L inverse into U for convergence for Gauss-Seidel method. But for convergence of Jacobi method, you have just a notation again, some P, okay, equal to minus, you have the same kind of minus. There it was I plus L inverse into U. Here, D inverse into L plus U. D inverse into L plus U. So here, the decomposition will be D plus L plus U. Unlike your I plus L plus U, here you have D plus L plus U. Here, D is nothing but your diagonal matrix. Diagonal matrix will be only principal diagonal entries you will have 5 minus 8, 4. Other entries will be 0. That is what you mean by diagonal matrix. Only principal diagonal elements will be there. Other elements will be zeros. Your L as usual and U as usual. So you know how to find L plus U. And D, as before, as I said, you will find its inverse. 1 by determinant D into adjoint D. So minus, you have D inverse. D inverse. I have found the same thing. Okay. So it is 0.2, 0, 0, 0, minus 0.125, then 0, 0, 0, 0.25. Okay. Into L plus U. L plus U, you can easily find out. L will be, what is L? What will be your L? What will be your L? Principal below only you will have elements. That is, you will have 2, minus 2, 0 in your lower triangle. and principal diagonal elements will all be zeros, and upper triangular element portions will be zeros. Plus U, similarly, you have principal diagonal zeros, lower portion 0, upper portion -1, 3 in the first row, 1 in the second row. So if you add D plus L plus U, you will get your original matrix A, 5 -1 3, 2 -8 1, -2 0 4. You can check. So this is how you find the inverse of D diagonal matrix, and L plus U you can easily find the product. Then you have this way. Okay. D inverse into L plus U, this much. So you take norm P. Here, remember, for convergence of Gauss-Seidel method, you are taking norm C suffix 2. For convergence of Jacobi method, you are taking norm P suffix infinity. Norm P suffix infinity. That way you have to remember. So P and C are just notation. But what is C? Minus of I plus L inverse into U in Gauss-Seidel case. In Gauss-Jacobi case, P is minus D inverse into L plus U. Okay, right. So norm P suffix infinity. What is suffix infinity? We call row sum. Maximum of absolute row sum. Just find out. Just find out maximum of row sum 0 plus 0.2 absolute value plus 0.6. So you get 0.8. Second row 0.25 plus 0.125, 0.375. Third row 0.5 plus 0. So you have maximum of absolute values of the sum of row, each row 0.8, 0.375, 0.5, which is greater 0.8. So norm P suffix infinity is 0.8, which is less than 1. Okay. So test of for both Gauss-Seidel and Gauss-Jacobi methods, the test of convergence is norm of the particular matrix is less than 1. For Gauss-Seidel, it is suffix 2. For Gauss-Jacobi, it is suffix infinity, where norm of C for Gauss-Seidel, which is minus of I plus L inverse into U, and for P for Gauss-Jacobi, norm P is nothing but minus D inverse into L plus U. Okay. That's all. So here you can, of course, you are given a condition that apply the Jacobi method to the system. You can using the initial approximation. So and show that the method diverges. Okay, you can easily check that. You will get the initial approximation. If you put 0 0, you get x1 minus 4, x2 minus x. And number of approximations, if you do, you are able to see that 0 minus 4 minus 34 minus 74, etc. etc. So any method you use, Gauss-Jacobi or Gauss-Seidel, the values are increasing. Gauss-Jacobi, Gauss-Seidel, you can see. So it is divergent. Okay, right. That's an exercise. Okay, thank you for your patient hearing. Even after 15-16 minutes, more than the prescribed time.
No
Thank
issues,
you.
sir.
Okay, thank you.
Yeah. Thanks. Have a great day.
Thanks.
Bye.
Thank you. Thank you.